for coming, and thanks very much for having me. I'm Hongyu. I'm a second-year master's student in the group. Today, I'm very excited to talk to you about our work, fine-grained energy attribution for multi-tenancy. And this is a joint work with our beautiful Michal and Theo. Okay. First of all, I'd like to give you a bit of context of this project. Initially, this was a side project, and we were brought together by our common interest in sustainable computing. And it's been a very rewarding journey. So the preliminary results were published at Whole Carbon this year, and in January, in July, and we have ongoing collaboration in academia, and also the theoretical model was adopted by a startup. And we also, this project was also sparkling the some thesis initiatives in the group, for example, with Milena. And also it was covered by a podcast from the Green Software Foundation as well. So lots of exciting stuff. I saw there's a question. Sorry, I can't see my mouse. So yeah, so lots of exciting stuff. Let's get into it. First of all, I will introduce the theoretical model that we developed for threat level NUMA-aware energy attribution, how it works, why it's important. And also I will show some initial results on validating the model, and as well as the effectiveness and robustness in a multi-tenant environment. Next, I will do a live demo inspired by Nicholas' talk from last semester. I think it might be fun to have something presenting live. And I will also introduce the challenges and opportunities towards the energy-aware cloud environment. Lastly, I will briefly touch upon our ongoing efforts to improve the ML training energy efficiency. Okay, and please feel free to interrupt me anytime you have any questions. Right. So, is there a way to get rid of the boxes? No. Okay, anyway. So I think just like any other environment-related talks, I feel it would be incomplete without showing you some humanity concerning statistics, right? So that's what I'm going to do. But I think it's really nothing new, right? Ever since Dennard scaling ended more than a decade ago, this has really put Moore's law to a slow death, right? It's still going, but although we can still build larger and more beefy chips, and we can cram more transistor onto it, the energy, the power density can no longer be curbed, right? So we can no longer gain performance for free without consuming more energy. Consequently, we now have huge amount of computing, environment footprints, and this is equivalent to the entire aviation industry nowadays. And furthermore, we now have increasing computing demand, right? Especially networking infrastructure. This is a huge energy consumer, and 4G coverage is going to be 100% in 5 years, for example. And we have machine learning applications, right? You see the exclamation mark there. And for example, training GPT-3 costs the energy consumption equivalent to 100 years of an American household energy electricity usage, which is very dramatic. So at this point, you might be skeptical as to, what's wrong with like pursuing better performance, right? That's what we've been doing. We're trying to finish our job as soon as possible so that we can save more energy, right? To be more efficient. What's wrong with that? Any ideas why we can't just optimize for the best performance?
Optimize for the best performance while keeping the energy low?
Yeah.
I mean, usually when you push your CPU or FPGA or GPU,
right,
power up all the transistors that are there, so you consume a lot of energy. So it's just like you have to do it efficiently from the code perspective. Otherwise, yeah.
I think that's a really excellent point. Yes, so that's exactly what I like to mention, because performance is not energy efficiency. And this is because of the power law, right? The power is proportional to voltage to the power times frequency plus the idle power. So if we were to optimize solely for performance, like just mentioned, then the time only has a linear effect on the total energy consumption, right? But if we were to power up all the transistors and increase our frequency, then this would have a quadratic effect on the overall energy consumption because frequency increases with voltage. That's physics, and that's why we really need. If we were to like optimize for like energy and performance, we want to make the trade-off between performance and energy. For example, all kinds of DVFS algorithms, dynamics voltage frequency scaling algorithms on Linux. Then we need the observability, right, on the user side, right? We need to know, given a certain energy budget, how much improvement between our version 1 and version 2 of our program. And the objective here can be the throughputs, can be validation accuracy, and so on. And then this information is fed back to the user, and so the user can, based on this information, improve their program for both energy efficiency and performance. And then that's really motivates our work for this per workload energy attribution. And specifically in this talk, we will be focusing on CPU and DRAM energy attribution. Okay. Yes. So what is software energy attribution anyway? So software energy attribution is nothing but determining the amount of energy used by your program and only your program, right? For example, on your server, you can I have my program, and my program is collocated with a bunch of other programs X, Y, Z. And in this case, I only want to, measure the program of my energy consumption, right? And exclude the energy consumption of other programs. But there are a couple of challenges preventing us from achieving this goal, right? The first challenge is this non-linearity in energy modeling, right? For example, we have a bunch of proxy statistics in, for example, utilization, the CPU time, DRAM utilization, stuff like that. And the mapping from those statistics to power is nonlinear by nature, right? And this is exacerbated by the NUMA architecture, where we have multiple CPU nodes, and each of which is attached to a bunch of DRAM banks, right? And in this case, each device would have a different curve, and at different points in time, this mapping would be different, right? So we can't really aggregate all of them to different sockets together, because that would lose the detailed information as to which points in time the energy mapping is. And also we have multi-threading, right? My program can sprout over different nodes, and also we have multi-tenancy, and my threads or my tasks can be collocated with that of other users as well. And we have runtime dynamics, right? Threads and processes can be created and destroyed at runtime, and so that we need to closely track the dynamics so that we don't attribute energy to some ghost tasks that have been finished. And we want a low-cost measurement, because we don't want our energy measurement, the model on the cluster, to consume more energy than my application, than the target application is measuring. All right. And so there are lots of available open source tools already for measuring the energy consumption. So we're not only the people who are working on this problem, but the key challenge is really the coarse-grained model they are having. So by coarse-grained specifically, I mean they're aggregating over devices. For example, we have multiple CPU sockets, and they are aggregating at any point in time the energy consumption over multiple devices, multiple sockets. And they are having, by the same token, have process level aggregation. For each process, there might be multiple threads. But if we were to only account for the process or aggregate the energy consumption of multiple threads, we're losing the information of every of the energy statistic or characteristics of every thread. And they have static tracking. There might be ghost targets as well. And the model energy modeling, as we can see, an orange box there. There also a attribution model running on the same cluster. And I wouldn't know if I were to use their tools, how much portion of energy is attributed to my program and how much was consumed by the attribution model on the cluster. And finally, similarly, it's also susceptible to noisy neighbor effect. If there are a bunch of other programs, then I wouldn't be able to determine the energy consumption of my own program. Okay. Right. And honestly, we can't really blame all these problems on these tools on existing work, because the key challenge or the key culprit here is really the hardware support, right? We're having very coarse-grained hardware support. For example, in a cluster, nowadays we're having very heterogeneous devices. And in this case, we can have CPU, GPU, and different disaggregated storage. Thank you. And the problem here is that the device only provides a huge battery from the user point of view, right? For example, Intel provides socket level energy reporting, and for GPUs, NVML is providing user level energy measurements, and also we have FPGAs, FPX. So it's very coarse-grained. And the question here is that, are we doomed, right? Software is ultimately depending on what the information provided by hardware. And in this work, what we are arguing is that no, fine-grained energy attribution is still possible even with coarse hardware support. And specifically, we mean that we are providing per socket accounting to account for the NUMA effect, the imbalance in resource allocation. And we have thread level attribution for multi-threading. We have dynamic runtime tracking, and we are robust. Our model is robust to noisy neighbor effect. For example, Tom is listening to the music on the cluster and I'm training model, then I'm still getting the energy attribution for my model only. And we separate our model, the energy consumed by our model from the energy consumed by the target. So the users would know that how much energy overhead this attribution model had. Okay, so really exciting, right? That's why I'm going to talk in details. It's a very busy slide, but I will going to dive into details of every symbol, how it works and why they are robust. Maybe let's start from the right-hand corner. This formula, or probably not. I don't want to put all of you to sleep, especially after lunch. What I wanted to show is that our model fits on one slide, which is good. So in this talk, I will only cover 2 points. One is the fine-grained CPU energy attribution model, and the second is how we use this credit-based mechanism to circumvent this noisy neighbor effect in a multi-tenant environment. Okay. Right. First, I'd like to, before delving into the details, I'd like to give you a high-level intuition and our principles in our model. So in this case, we have our server and multiple sockets, and I have my program running and a collocated program X, and we have our energy attribution model there. And the first step is to separate the static power from the dynamic power. And this is also one of the common pitfalls in prior work. So the static power is the power, the minimum power that is sustaining your laptop or a server to be active, right? Not to be confused this with the static power with the idle power. So the idle power, for example, on Intel chips, they would have multiple P states, that the passive states, that basically that represents the states where your laptop or the server is sleeping. What we are mentioning is the static power, where the minimum power to maintain your kernel or all kinds of daemon processes and so on. What we are targeting is the delta part, right? Is the dynamic portion. And we want to attribute this dynamic portion to different workloads on the server. And secondly, as we've mentioned, we want to take into account the spreading of different threads on different sockets, as well as the threads from the collocated program X. And given the thread and their resource usage, especially the exclusive resource usage. By exclusive, I mean the resource used by only the brew threads instead of the red thread. And given the resource usage, we assign the energy credits to each of the program so that we can distribute the delta dynamic portion of the energy. Finally, in order to separate the energy consumed by the model, we also assign the credits to the attribution model as well. Everything clear so far? Right. So let's delve into the details. What do we do? First, we measure the delta energy. So ahead of time, we'll sample the static energy of the server on socket S, so the small s, and we subtract this static energy from the total energy to get the delta energy back. Second, we estimate the so-called CPU residence rate. What I mean by that, for every single thread, small a, for the application A, the calligraphic A here. And this is basically computing the probability, the conditional probability given a task to be this task to be scheduled on socket S during the sampling period. And in terms of implementation, this would translate to sampling the scheduling decision of the kernel for this task on socket S. Right. And the third step would be estimating the time our application has spent on socket S. What we do is that we use the conditional probability to aggregate over all the tasks of our application to distribute the runtime to different sockets so that we arrived at a conditional expectation of our task running on the server. Right. Next, what we want to do is to get the per workload energy credits. So how do we do that? First, we want to get the global resource usage, right? So the overall system-wide CPU time on socket S, so this T total S there, and then we compute the CPU energy credit. What I mean by that is nothing but a fraction. So it's the CPU time of our application on socket S over the CPU time of the total application, the total CPU time of socket S scaled by a nonlinear factor gamma between 0 and 1. And over the time, this would translate to a piecewise nonlinear function to account for the nonlinearity between the proxy statistics, in this case, our utilization, to the total energy consumption. And this is what we call the CPU credits here. Yeah, that's the gamma. And now we have our CPU energy credits. What we do is that we want to distribute our delta energy to different workloads on the server. So how do we do that? Is that we leverage these energy credits, which is a fraction. We distribute this energy for every single socket, every single node on our cluster, plus the static power. Then we arrived at the total energy of our application of the CPU energy. Questions? Yeah.
Well, and we know if we process it on the FPU floating point unit,
yeah,
and the Boolean logic or integer logic, the energy are different.
Yeah.
If you measure based on the proportion of the CPU time,
Yeah.
then I think there may be some variation with specific process unit you use.
Right. Right. So if I understood correctly, the question is, so there are different ALUs on the chip. We have integer process units, add, and also we have floating point arithmetic units. And definitely like floating point arithmetic units are much more expensive, right? Much more complicated, and their energy consumption is definitely larger than those integer ones. And the question is, if we were to only use the time and or the utilization as a proxy, wouldn't we lose like detailed or more like granularity there? Is that the question? I think that's a really great point. So here, as I've mentioned, indeed, we are definitely losing accuracy there. And the point here is that we are trading the performance of the energy attribution model and the preciseness of our model. So in terms of energy consumption, each floating point unit is like picojoules. It's very small. The difference between integer add and floating point add on the larger scale is relatively small. But the sampling of the energy consumption for each and every floating point operation is very expensive over a period of time, for example, a 1 hour training. So I think definitely it would be better it would be more ideal to sample every single operation. But in order to be for this model to be feasible, we trade off the performance with the preciseness. But that's a really good point. Thank you. All right. Question.
The question about the non-linearity that you have here.
Yeah.
Does that mean that if I run my workload or my program once on a system that is not heavily used and once where it is heavily used, and that is already heavily used by other workloads, then I essentially get a worse energy attribution on the one that is already used more than on the one that is not really heavily used.
Right. I see. So thanks for the question, Nicholas. So the question is, for the nonlinearity, does that mean that, so for example, we have two servers, one is heavily utilized, like 99% utilized, another is like 10% utilization. And would that be different if we were to measure the energy consumption of the same work on different servers? That's a really great point. There's a concept called energy proportionality, meaning that the energy is scaling not linear to the utilization. So basically what it does, well, from my observation, what it does is that at the beginning, the energy shoots up very quickly. But when it's approaching to the maximum utilization, this levels off very quickly. And whether you will get a worse energy attribution, I would say it's actually better, because the energy proportionality says that basically when you have very low utilization, this you have actually a lot more energy consumption. So this is disproportionate. So the ideal version would be if we have 20% utilization, the energy to the maximum power would be 20%, right? But in fact, when we have only 10% server utilized, we will have almost 70% to the maximum power utilized. So it's disproportionate. And it's actually better to have you on a more utilized server than a underutilized server.
So the general point is that based on the load of the server itself, I can get a different attribution for my own workload.
That's exactly true. Yeah, thank you. Right. So yeah, so the DRAM model works similarly to a certain degree of nuances. Well, we want to do next is really to validate our fine-grained model, right? So the setup here is, so to validate our theoretical model, we provide a prototype implementation called Energy. It's available on GitHub. And we also construct 4 micro benchmarks acting as the target application, right? The CPU benchmark exercises the CPU from 0 to 100% utilization. The MEM benchmark stresses the memory from 0 to 100% with one process as well. And the mixed benchmark basically uses both the MEM and CPU benchmark to maintain roughly the CPU energy, the utilization of both DRAM and CPU at approximately 50%. And then at last, we have the mixed with neighbor. So basically, this is launching 2 parallel mixed workloads. One is the target application for which we are measuring the energy consumption. Another is the neighboring, a noisy neighbor, as a noisy neighbor, like a multi-tenant environment. But we are not measuring the energy consumption or attributing the energy consumption for the noisy neighbor. And the purpose here is twofold, right? One is to cover all utilization levels so that we can make sure that our model is doing the right thing across all the proxy statistics. And the second is to mimic the noisy neighbor effect. And our testbed is a dual socket server with 32 cores and 64 gigabytes of DRAM. So first, we want to do is to validate our model. And in fact, this was the most difficult part in the whole experiment, because validating this fine-grained task level energy attribution turns out to be really difficult. And after delving into the literature, I found that it's impossible actually to validate directly the energy attribution model. That's why I turned to a method called validation by summation. So the intuition here is that on a server, say we have hundreds of tasks running, and what we do is that we attribute energy for each and every single kernel thread or task. And we do this individually and independently for every single task. And at the end, in parallel, what we also do is to measure the total energy consumption of the whole server. So at the end, we compare the sum of all the attributed energy for every single task with the total energy of the server. If they match, then our model is indirectly validated. And this is because we're doing this independently and individually for each task, and because of the nonlinearity of the modeling. So if our model is not doing the sensible stuff, then it's very unlikely that the summation will be the same as the total energy consumption. Okay. Yes, that's why I modified a Firefox plugin. I've modified a Firefox plugin to make it free running as the reference value to measure the total energy consumption. And yes, so the blue box here highlighting the total energy consumption of the server, and EnergyAt alongside is also measuring the total energy consumption as well. And this part is the attributed energy to the all the tasks like system D and the micro benchmarks and the aggregated energy portion.
Okay, what tool do you actually use under the hood to, like, are you probing this some way, or like, do you need a special server that you have physical access to do this, or what tools under the hood actually do that?
Right. So the question is, what tools are we using to get the energy measurements from the hardware, or what software we're using to aggregate the tools?
The hardware. You said it's coarse-grained, but what are the attributes?
Yes, I think, yeah, at the end, yes, we have. Yes, it's the hardware counter we're sampling. So basically, we're using the Intel RAPL counter. Oh yes, yes. The Intel RAPL counter to sample the per socket the socket level energy measurements from the hardware. Yeah, but the energy attribution model is implemented in our prototype EnergyAt. Yeah, thank you for the question. Yes. And the dark part is the cost of our energy attribution model. So this is the software cost when we are doing the system call to get the register values from the Intel registers. And that's the part we are having the overhead. And that's also ties back to the previous question, why we're not doing like per flop measurement. That's because that would be extremely expensive for a like heavy lifting workload. Yes, so a couple of observations I'd like to highlight. First, the total value here. So the total energy consumption of the server is approximately the same as the reference value. At least Energy is measuring this more or less the same value in terms of total energy consumption. And the sum of the attributed energies plus the cost of measuring the energy consumption is the same as the total energy consumption value. So this is the indirect validation I was mentioning above. And one caveat here is that, as you can see, the memory, there is a slight underestimation in terms on the memory benchmark. And this is because we are only measuring the shared memory, sorry, the private memory to each thread or each kernel task, and excluding the shared memory, like the shared libraries, runtime linked libraries, which are very hard to reason about as to how much portion each task should be accounted for. Right. Next, what I'd like to show is the CPU credits I described in the formal formulation in action. So in this case, on the axis we have the time in seconds. On the right hand side, the right hand side we have the plot for the CPU credits that I just mentioned, CPU energy credits, and on the left hand side. Sorry, that's the right hand side on your side. That's the total energy consumption for that application. Okay, so the blue lines, the wiggle blue lines, is the energy measurement or the statistics we measured for the mixed workloads, keeping a 50% utilization across time, if you can recall. And for the orange line is the mix with neighbor workload, meaning that we are measuring still the mix micro benchmark, but in the background we are launching a neighboring attack, not a neighboring attack, but a neighboring task. So what we do is that at the beginning, in the middle of the running, we start a neighboring task to temper the resource utilization, the energy measurement. So in this case, we can see a sudden drop in the energy credits. Why is that? This is because the server total power will increase because of the addition of an workload. Right, the total energy consumption increases, but the share of our energy consumption of our application stays the same. Theoretically, should stay the same because our workload is not changing. The only thing changes is the addition of a neighboring task. And although the total energy consumption shoots up, our attributed portion of energy should drops down in reaction to the addition. And because of this mechanism, we can see the attributed energy stays roughly the same, regardless of whether we have a neighboring task or not. Although there's still a slight dip, but more or less it's unaffected. Question?
But couldn't the neighbor task increase the energy usage of the targeted task? Like you might get a lot more DRAM misses because due to interference?
Yes, that's a good point. So the question is, wouldn't that be possible when we have more workloads running, then we have all kinds of issues like cache thrashing, shutdown, and resource contention. Therefore, we will have more operations and higher energy consumption. I think that's a really fair point because that's actually what would happen in the cloud. And that's also one of the reasons why I kept the workloads being resource consumption around 50% instead of 60% to create this intentional resource contention. But I think on the other note, in the cloud, if you were to run your program and you don't want your energy credit to be affected by neighboring task. I think that's also one of the reasons why, yeah, we want to have this reactive mechanism here as well. But yeah, that's a really fair point. All right. Yeah. Finally, we also wanted to compare with prior work. So in this case, it's a busy plot. Let me break it down for you. First, we also have the total energy consumption there in the upper part. Below is the attributed energy from different tools, available tools, including Energy At, our prototype implementation in Grain. And what I like to draw attention to are several observations. First, using Energy At as a reference point, we can see there is a substantial overestimation and also huge underestimation as well. And they really, different tools really give very dramatically different measurements to the user, right? If I were to the user, I wouldn't be able to consistently optimize my program for both energy efficiency and performance. And secondly, when comparing mixed and mixed with neighbor workloads, we can see the addition of the mixed workloads can really affect the energy attribution from different tools. As we can see, Energy At is more or less unchanged between with or without a noisy neighbor task, but other tools can have very different measurements. Yeah, so that's a good point. So CPU, MEM, and mix, these are single tenant workloads.
How do you know the ground truth? Like, how do you know these other two?
That's a good point. So the question is, how do we know the ground truth of whether it's underestimating or overestimating? The short answer is we don't know. The long answer is, first, we're using Energy At as a reference point because we first do the validation first, and then we do the comparison. So we are assuming that, yeah, our prototype implementation is relatively accurate. And the second point, we can see that they are exceeding even the total energy consumption of the overall.
If I understand correctly, Energy At is mostly about taking measurements that from the hardware that are for like the whole machine, all the cores, all the DRAM, etc., and figuring out what's the right attribution. Multiple workloads might be actually running there.
Right.
But it starts by assuming that, yeah, I mean, here if it's just one workload, you attribute everything to it, right? Or are you trying to like figure out the user versus the OS components or something?
Yes, that's
other tools saying it's not graphical. So why would they get such results? It's just single points.
exactly. Okay. So there are two parts in the question. The first part is, so if it's single workload, what's actually different in our model compared to other tools are doing? The second is, if the as you can see, there are other tools also underestimating and overestimating what like the kind of hardware infrastructure they are using to measure the energy consumption. Yes, so for the first question, I think, so yeah, what was the first? Yeah, so for the first question, yes, there is only a single workload that we are measuring, but indeed, as Anna has pointed out, there are also kernel background threads running as well. And also, although there is a single workload only, but remember for CPU, we have like 10 threads, or sorry, in that case, we have 16 threads running. So each and every thread is measured independently and individually. So we're aggregating the energy consumption over multiple threads. So that's also one of the difficulties as well. Secondly, yes, we also need to separate our energy consumption from the energy consumption from the overall infrastructure, for example, the kernel tasks. And for the second question, actually, I've looked into the implementation of other tools. They are all using Intel REPL meters and those registers to get the energy measurement. And you might ask why they are having this overestimation and underestimation. I honestly think it's an implementation thing. Some of them, that's why we are first validating the total energy attribution, because we want to know that the total amount of energy we've sampled and aggregated over time from our formula is the same as the total energy consumption. Instead of we are off from. Exactly, yes. The total would include all the tasks of that server. And I think, so there are some problems. So I can give an example where this can go wrong. So the register values don't have a maximum limit. So when this maximum limit is exceeded, for example, over an hour of measurement, this will wrap around. And in the implementation, you need to take this into account as well. And not all the tools are taking this into account. And that could cause impreciseness as well. But that's only one of the reasons why there are impreciseness in measurements. Yeah, question? Yeah.
Could you also use these other tools to measure the total amount? Because I guess like here it's quite visible that Carbon Tracker and Code Carbon, they're definitely overestimating because they're using more than what the total is even using. While the other ones, the OS could just be really doing something that is very expensive during that period, and they could still be right.
Yeah, I think that's a really fair point. So if I understood correctly, the question is, so could we also use other tools to measure the total energy consumption when they are running? And because different attribution mechanism, they could have used a lot more infrastructure and cost a lot more energy consumption. Is that what you are mentioning?
Yes, I guess the first part is the important one. Could you also use the other tools to measure the total amount?
I think yes. The question is yes, you can. So the answer is yes, you can use other tools to measure the energy consumption as well. But the key point here is that they don't provide this kind of mechanism out of box. So in our prototype implementation, the only thing you need to do is to give PID being 1, so the system D, and then the tool will automatically track all the child processes and threads it's spawned from there. But for other tools, it's more complicated than that. That's why for fairness, we use the Firefox plugin, which was a public tool integrated with the browser to measure the total energy consumption. In fact, this is not this energy consumption is the average. So we average over several runs, and this is the energy consumption when running all the when running each and every tools. So the energy consumption is roughly the same across different tools. So we do that to make sure that at least that's a sanity check. But yeah, that's a really good point as well. All right, so next, I will do a live demo. Hopefully everything works. But very quickly, let me check the time. Okay, we are already over time, but I will do this very quickly. Oops. This is very weird. I can't see half of my screen. Maybe this works. Okay.
I think you may also need to share an option because it says that, I mean, for people on Zoom can just.
That's a good point. Thank you. Share. Let's share the overall screen. Yeah. So what I'm going to do is that I'm going to log into a bare metal machine. So on this machine, the first thing we do is that we pip installs Energy, right? And sudo here is very important because we need the root permission to access the hardware counters. Ignore the warnings. And then let's check the on Tmax where I have 4 windows. The Energy, which is where we will run our tool. My application will be running on this window, and the neighbor will run another window. And the top basically is a the monitoring window we're measuring. So on the server, we have 32 cores, and we have nothing running but the background kernel. And what we do is that I will just first, what I'm going to do is to start my application. So in this by application, I will just simply run stress ng with 15 threads and 30 gigabytes of memory. So let's start that. And then we have the PID of that task, right? So what we do is that we provide the PID to Energet. So we sudo Energet, we log at the debugging level, and we log out every 2 seconds some outputs, and we start it. And at the start, it will add all kinds of child processes and kernel threads. And what this is doing is that, as we can see, this is attributing the energy consumption to every single process. So we can see the memory fraction, the memory credits is 90%. The CPU credits is also almost 100% as well on socket 1. And on socket 0, we are using, this is the tracer. So basically, this is the energy attribution model we are measuring. This is the energy, we are using only 80% or almost 90% utilization on socket 0, and we are not using nothing, well, we're barely using any memory on socket 0. So there is an imbalance in memory allocation. And this is random, right? Okay, the stress ng is creating random workloads. So we can see the resource imbalance here. So what we do next, we launch a neighboring task, which is doing essentially the same thing, 15 threads with 30 gigabytes of memory. And suddenly what we can see from our terminal is that, let me check, our energy energy credit suddenly dropped to almost 20%, 2%. And also on socket 1, we are dropped to 70%. So this is reacting to the addition of a neighboring task. Okay. There are a lot more things I'd like to show, but given the time, we're already over time. Let me go back quickly to the presentation. Yes. So next, I will very quickly get rid of the chat. And very quickly touch upon the challenges and opportunities ahead towards achieving a heterogeneous energy-aware cloud environment. Oops. Yeah. First of all, is that we really need a software-hardware interface that helps us cross this hardware-software boundary to efficiently and securely get the energy reporting from different devices, right? Because as you've seen, we now still need the root permission and to do all kinds of system calls. And this really gives almost 10% of energy overhead when Energet is measuring the whole server, right? And second, the energy attribution for high-level cloud services, for example, function as a service or database as a service and so on. And virtualization here is really a key enemy because these services are 1,000 miles from the hardware, and adding a level of virtualization really messes things up. And we have heterogeneous devices, each of which has different energy characteristics. And if we were to able to have this precise energy attribution, we may enable energy-based billing, right? Energy is the second most costly resources when running a cloud data center, but now it's not being taken into account. We are still using memory or CPU, which is doubtfully the right way to do the charging. And we need, although currently we have the fine-grained energy attribution model, how we can leverage this to make energy-aware energy optimization. For example, we can have, should we spread our tasks to different cores on the same thread, on the same NUMA node, or we should utilize all the NUMA nodes, right? Finally, we believe that it's worth revisiting those traditional algorithms that are traditionally optimized only for performance. For example, is B-tree more efficient than a hash table in terms of energy consumption? Right. Finally, I'd like to also touch upon our ongoing work in terms of optimizing for machine learning training. So nowadays we have a whole bunch of machine learning model architectures, right? Transformers, RNN, and other traditional models, and each of which would have different configurations as well. And on the device side, we have a whole bunch of whole host of GPU devices as well, and each of which would have hardware knobs that we need to tune, like maximum power, frequency, stuff like that. And as we've mentioned before, performance is not energy efficiency, right? And this principle also applies to machine learning applications as well. So that's why what we want to do is that given a specific model, we want to find the best configuration for that model, whatever best would be. And we also want to automatically tune the GPU mode for a certain type of GPU for this machine learning training. And we want to do this without enumerating all the possible configurations and tasks, and to find the most energy efficient configuration. And yeah, this is a joint work with U of T, and I'm very excited. I'm really looking forward to what we can achieve here. And yeah, that concludes my talk. Please feel free to check out the code and our paper. And yeah, and also feel free to hit me up if you have any questions. And I also have some backup slides, so I'd love to take any questions. Thank you very much for your attention.